Despite all we've learned about the universe over the 20th and 21st centuries, a few important phenomena have yet to be sufficiently explained. We know there's more matter than antimatter in the universe, but we don't know how this cosmic asymmetry came to be. We know that for every gram of matter in the universe, there are 5 grams of dark matter, but we don't know what dark matter is or what its properties are. And we know that the universe's expansion is accelerating, but we don't understand what's causing that phenomenon. We've given it a name, dark energy, but lack an understanding of why it exists at all, and how it came to have the value it possesses today. In a fascinating new study that's taking the internet by storm, a team of scientists believe they've found a connection between the interiors of supermassive black holes and the dark energy that permeates the universe. For a full century now, ever since the 1923 observations that allowed us to first measure the distances to galaxies beyond the Milky Way, we've noticed an important relationship. The farther away a galaxy is from us, the faster it appears to be receding from us. When we made the connection of these observations to Einstein's general relativity, we discovered that the universe was expanding. It was like a great cosmic race was taking place between the initial expansion driving everything apart and the gravitational effects of all the matter and energy in the universe attempting to pull everything back together, where the Big Bang was the starting gun. For many generations, physicists and astronomers considered 3 main possibilities for how this race would end. A big crunch. After a period of rapid expansion, there could be enough matter and energy in the universe to cause the expansion to slow, stop, reverse direction, and recollapse, ending in a big crunch, a big freeze. In this scenario, the universe begins expanding rapidly, but now there isn't enough matter and energy to cause the expansion to stop and reverse. Instead, it expands forever, with all the matter structures within the universe eventually coasting away from all the others, where the universe would recollapse if there were a single extra atom in it. But instead, the expansion rate only approaches 0, never quite stopping or reversing. And yet, when the definitive data arrived in the 1990s, it indicated that the universe was actually doing none of these. Instead, after looking like it was on track for a Goldilocks ending for several billion years, distant galaxies all of a sudden started speeding up in their recession from one another. The expansion of the universe was accelerating, and that required a new type of energy that was different from all the known forms of matter and radiation, something we named, for better or worse, dark energy. As our measurements of the distant, expanding universe improved, we found that dark energy behaved in a specific manner, as though it were a form of energy inherent to space itself, behaving equivalently to Einstein's cosmological constant in general relativity. This was beyond puzzling. It was baffling. If there were a cosmological constant present, it comes without explanation for why it's non-zero or how it got to have the value that it does. If we attempt to calculate the zero-point energy of space using quantum field theory, we get nonsense answers that are 10 power 120 times too large. Many have assumed that this is simply evidence that we don't know how to calculate the zero-point energy, and that it must all cancel away, equaling 0 after all. But then what causes dark energy? Why does it behave as though it's some form of energy inherent to space itself, rather than diluting like matter or radiation does? Although many new hypotheses have emerged, a new field, a new parameter, or some other type of new physics, no evidence has emerged supporting any of them. One interesting idea that was explored at length in the mid-2000s was the idea that dark energy could have arisen due to the negative binding energy that resulted from the formation of stars, galaxies, galaxy clusters, and the Great Cosmic Web. The equations that we use to calculate how the universe expands assume that the universe obeys the cosmological principle, that it's isotropic, the same in all directions, and homogeneous, the same in all locations, everywhere. This is accurate if you smear out the cosmic web. The average density in a region of space 1 billion or more light years in radius is pretty much the same everywhere. But on smaller scales, it's very clear this assumption is invalid. A fun calculation that one can do, and that I myself did in a paper back at that time, is to actually quantify the effects of this inhomogeneity energy and see how it behaves. It turns out that you can quantify the gravitational potential energy, the inhomogeneity energy, and the kinetic energy arising from gravitational imperfections or the departure from perfect smoothness at all times in the universe. Those curves not only never rise above the 0.1% level in terms of how they affect the universe, but even irrespective of that, they never behave as dark energy does, as a cosmological constant or some other form of energy inherent to space itself. The only place left where there was any wiggle room for this sort of effect to occur, what we call a back reaction effect, because it would be an effect that arises as the universe responds in an oppositional way to something that occurs within it, would occur where singularities arose, in the interiors of black holes. That kind of treatment went beyond what anyone knew how to calculate, but it was difficult to imagine that black holes would matter very much for three reasons. For one, we can quantify how much gravitational binding energy there is in black holes, and it's only about 0.01% of the needed amount of energy to explain dark energy. For another, the dark energy density needs to remain constant over time, but the number density and mass density of black holes decreases over time, especially at very late times. And for yet another, individual black holes actually grow over time, and new black holes continuously form, but this growth occurs much more slowly than the rate at which the universe expands. Although no one had been able to do a full calculation for how does the energy in black holes contribute to the expansion of the universe, the way we've been able to do it for other contributions, it didn't seem like a very compelling pathway, which is why it was an absolute shock to see the headline appear, just days ago, that black holes are the source of dark energy. Even more surprisingly, at least to me, was that when I went into the scientific paper itself, was that this was based not on a theoretical calculation, but rather on observational evidence, which was absolutely shocking to see. The overall claim is that black holes, and specifically supermassive black holes, couple to the universe's expansion on the largest cosmic scales, and that the specific way that they must couple could potentially explain some or even all of the dark energy effects we observe. What did they observe? What does it imply? And how does the black hole dark energy connection work? They start by reminding us that based on what we've seen from black holes on all scales, including from stellar mass black holes that merge and emit gravitational waves, from the direct observations of the photons bent around a black hole's event horizon, and from hot plasma, gas, and stars seen in orbit, and the light they emit around supermassive black holes at the centers of galaxies, we know that the realistic black holes we have in the universe typically rotate extremely rapidly, close to the speed of light. This means that their singularities are not just point masses on the inside, but they have spin-angular momentum as well, which means they have complex interior geometries in general relativity, given by the Kerr solution. All of that is fine, but general relativity is notoriously difficult to work with, particularly if your system is complicated in terms of what's at play in your universe. For example, if all you have is empty, unchanging space with no matter or energy in it, your spacetime is simply flat. The same spacetime we have in special relativity, with no gravitational effects. If you put down one point mass that doesn't spin, you get the spacetime for a black hole with a spherical event horizon, a Schwarzschild black hole. If you put down a point mass that does spin, you get the aforementioned and illustrated above Kerr black hole. And if you try to put down a second point mass in either the rotating or the non-rotating case, the equations become unsolvable. You can only approximate them using numerical techniques. The flat empty space solution was discovered by Hermann Minkowski, Einstein's physics teacher, back in 1908. The non-rotating point mass solution was discovered by Carl Schwarzschild in 1916, just months after Einstein introduced general relativity in its final form. The rotating point mass solution was discovered by Roy Kerr, who's still alive in 2023, back in 1963, and who many believe should have won a share of the Nobel Prize awarded in 2020 for black holes. And the fact that two masses cannot be solved except via numerical approximation techniques has been a well-known phenomenon for generations. If it teaches you anything, it's that general relativity is very hard. One of the exact solutions that's been discovered is for a universe with a cosmological constant, the equivalent of dark energy. It's known as the de Sitter solution. Another is for a universe that's uniformly filled with matter, radiation, and any other form of energy, the generic solution for an expanding or contracting universe. It's known as the Friedmann-Lemaître-Robertson-Walker solution. Now here's a fun, or not so fun fact. You can combine the point mass and the cosmological constant solutions together and get a spacetime known as Schwarzschild-de. You can also put the rotating point mass and the cosmological constant solutions together to get a Kerr-de solution. But we live in an expanding universe with a cosmological constant, matter, and radiation, and need the full Friedmann-Lemaître-Robertson-Walker solution, and would like to combine that with the Kerr solution by embedding a rotating point mass within it. That's something we really don't know how to do. We don't have an exact solution for that at all. But this is precisely what the new paper is about, attempting to make this connection in a reasonable and consistent way, and to tie the growth of realistic Kerr black holes to the overall expansion of the universe, even arbitrarily far away from the black hole itself. How do you do this? The approach the authors take is as follows. They look at multiple samples of elliptical galaxies from across cosmic time, nearby modern galaxies, galaxies from 6.6 billion years ago, galaxies from 7.2 billion years ago, and galaxies from approximately 6 billion years ago. They assume that there's a universal relationship between the mass of the central black hole and the mass of the stars within a galaxy, which can evolve over cosmic time but should be universal at any particular time. Then they use their model of cosmological coupling, assuming there exists a relationship between the mass of a black hole at any particular cosmic time, or, more accurately, redshift, and the mass of the black hole at the time it becomes cosmically coupled to the expansion rate. If k equals 0, the minimum allowable value, then there's no coupling and the mass of the black hole you infer doesn't change with time or affect the cosmic expansion. If k equals 3, then the coupling is at the maximum allowable value, and the mass of the black hole increases as the cube of the redshift ratio, and the black hole acts like it causes dark energy. And if k is anywhere in between those values, then the mass of the black hole grows, then the mass of the black hole grows, and the black hole behaves as something that contributes to the expansion of the universe, but neither as matter nor as dark energy. They leverage the various samples they chose and assert that if they find the same coupling ratio, k, across all of the different samples, then this picture is valid and it ws us to observationally determine how black holes contribute to the universe's expansion, if, that is, you believe it. Do you? Thank you so much for coming this far with us. Remember to join us in the next video. Until then, good night, and remember to dream big.